Today we have the pleasure of having Professor William Unruh with us. Unruh has been to Brazil a few times, and he couldn't be today with us in person, but he's going to give this talk to us. And Unruh is a professor of physics at the University of British Columbia, and his research includes contributions to general relativity and foundations of quantum mechanics in relation to black holes. He's a fellow of the Royal Society of both London and Canada, and has several titles. He's here to give us this talk about time and quantum gravity. Thank you very much, Professor, and let's get started.
Okay, thank you very much. I'm really sorry that I can't be there. I had a clash, and in some sense it turned out the clash disappeared because of various problems. But anyway, I'm glad that I can be here, at least virtually. What I want to talk today about is, briefly, I will talk a little bit on the topic of the meeting that you have, and then looking for a way out of the problem, set up the possibility that perhaps one shouldn't quantize gravity, and then talk about an experiment, namely LIGO, which throws, I think, a little bit of light as to whether or not that way out actually works experimentally. The answer will be no. Anyway, so as we all know, we have the constraint equation, the Hamiltonian for for gravity. Classical Hamiltonian has the form of some like Lagrange multipliers, n0 and ni, times operators, four operators at every single point in space-time. So this is, in a sense, an infinite dimensional constraint subspace. When we vary that with respect to n's, we find that h0 and hi are equal to 0. These are the so-called constraint equations. If you have matter, you get additional matter terms in the h0 and hi. Now, I've written the h0 and hi very symbolically because it's not going to matter. I'm just going to talk in some generality about this. The hi are the ones that, in the classical theory, generate spatial diffeomorphisms on the time equals constant slice, and h0 is the time-like diffeomorphisms which go off into the future. This causes a bit of trouble classically, but not all that much. These are just parts of the Einstein equations, four of Einstein's 10 equations, which express coordinate invariance of the theory. And if one replaces these n0 and ni by some functions, this is sort of a small temporal change in coordinates. This is a small spatial change in coordinates. Then these equations generate via the Poisson algebra the coordinate transformations. So, as many people say, these coordinate transformations look a lot like gauge transformations, just like the gauge transformation in electromagnetism, where A sub mu's are the fundamental variables in terms of which one writes the theory, but the A mu's are themselves not actually measurable. It's only things which are invariant under the gauge transformations that are generated that are measurable. Things like the magnetic field, the electric field, also integrals around a closed loop of these A mu's. The A mu's themselves are not measurable, if you will. They change when you do a gauge transformation, but that integral stays the same. And so it is also measurable, as Aharonov Bohm taught us. One of the things, just as a sidelight, one of the things that one has often heard claim is that Aharonov Bohm is a quantum phenomenon. It's not. It's one can express it in a purely classical terms as well. So how does that apply? Well, one of the things that you come out of these gauge transformations is that measurable quantities must be things that can commute with the constraints. In other words, if one does an infinitesimal coordinate transformation, for example, that's generated by these constraints, h0 and hi, at each point in space. And so they have to commute, and physical quantities therefore have to commute. Things which are actually measurable have to commute. After all, we do not want physical quantities to depend on the coordinate system. The answer one should get for physical things should always be independent of coordinates. And so one could quantize the whole thing with these, all of the metric components, etc. But most of them are sort of fake. The physical subspace of the Hilbert space has to be the subspace which is annihilated by the constraints. But if you have a quantity that does not commute with the constraints, then if I operate on the state with respect to that quantity, it will not stay within that physical subspace. In other words, it will produce vectors in this larger Hilbert space which stick out of that constraint subspace. One can think about, for example, saying, well, then the physical thing, what I do is I operate on the space state with one of these variables that does not commute with the constraints. It will therefore produce a vector in the Hilbert space, which partially may lie inside that constraint subspace, but it may also partially stick out of that constraint subspace. So all we do is we project back down into this constraint subspace. The problem is that then you find that there are almost an infinite number of operators that give the same projection. In other words, one can think of any operator that has the same component within the constraint subspace, but sticks up in all kinds of different directions out of the constraint subspace. That's just another way of saying that if something isn't physical, then it becomes completely ambiguous as to what that operator actually means. Oops, what happened? There we go. Another problem is that also one has not found a way of defining the operators in this canonical quantum gravity such that the constraints themselves are on shell. In other words, if you have something which obeys those constraints, when you commute the constraints with each other, they stick out of the subspace. So the constraints themselves, which are supposed to be zero, which is clearly an invariant thing, themselves create things which stick out of that constraint subspace, which is not good. One could try to produce even more constraints in order to get rid of that. The trouble in quantum gravity is that that whole process doesn't seem to end. Give us a little bit of a feeling of this. What this means is, let's take this Hamiltonian I have here. It's a harmonic oscillator. Capital P's and capital Q's are basically harmonic oscillators, momentum and position variables for a harmonic oscillator. Then we've got these two other operators, little p and capital T. Why do I call it capital T? Well, we'll soon see that. None of capital P, capital Q, or T commute with that Hamiltonian. Capital T is the conjugate variable to P. So P, T comma P is not equal to 0. However, it's very easy to find operators which do commute with this constraint. Namely, this operator down at the bottom, Q cos T plus P sine T. Well, come on. That just looks like the time dependence of the harmonic oscillator as a function of time, which is why I called it capital T. So here's a variable that does commute with the constraint, which is the equation of motion, which is the solution to the equation of motion for this constraint. Is that right? Well, actually, no. The problem with that is that very many people say, look, well, this tells us what is the correlation between Q and P, capital Q and capital P, and T will interpret the eigenvalues of T as the time. The problem is that T, P, and Q, none of them commute with the constraints, so they're not physical. They're not measurable. And the only thing you can say is that this combination of them does commute with the constraint, but it doesn't tell us anything about, what P and Q are at some time, which is, of course, what we're interested in. We're interested in the way in which the world changes in time. And our experience of the world is one in which, and our experience in physics in particular, is one in which one is looking for these correlations in time, which this doesn't give us, because none of the things that this equation of motion, that this particular solution, they don't tell us what happens at any particular time, because particular times are not defined. So T is not something like the time. It's not something that's measurable, and certainly for us, the passage of time is measurable. They're not physical quantities. So we have this one physical variable, this combination of them, but we can't interpret it as an equation of motion because we can't interpret the parts of it as being physical things that this is giving the correlations between. How does one get out of this? I mean, this problem has been there now for at least my whole career, and actually much longer than that. Is there a way out of it? Well, one of the ideas that Jonathan Oppenheim asked himself was, well, maybe one shouldn't quantize gravity. Gravity is classical, and everything else, of course, is quantum, because we've done lots of experiments which show that small systems behave quantum mechanically. How can one do that? Well, one of the things that one has often heard people talk about is, well, we do, semi-classical gravity, where we just take the quantum operators and take the expectation values of them. That's a classical quantity. That's just a number. And so we could stick it into the equations of motion and try and solve those. But that simply doesn't accord with what happens in the real world. You know, the moon is a quantum system. Over the whole history of the moon, its expectation value, or rather its the square of its the expectation value of the square, the fluctuations add up. And one would expect to see the moon, instead of being this one single thing there, the expectation value would look like the rings of Saturn instead. The moon's, completely uncertain as to where it is. Of course, we say, wait a minute, well, you do measurements on it, that projects it back down to, something that has an uncertainty, but it's so small, one quantum uncertainty, that one could never measure it for the moon. The problem is then you get a theory in which things go jumping around, which just doesn't seem to be the way in which things actually operate. In fact, Don Page did an experiment on this back in the 1970s, where he did a Cavendish experiment to try and see whether or not that Cavendish experiment depended on a quantum system. And he found no, that he still kept getting this reduction of the wave packet and these changes in the expectation values. So what I'm going to use this for is as an excuse to ask, well, is it even possible? Is there any evidence that one could regard part of a system as a classical system and the other part of it as a quantum system, as Jonathan has done for gravity? One cannot do any experiments with gravity. The effects are just simply far, far too small that one could see what the theory was like. Now, in his theory, the way in which the quantum system interacts with the classical system is that it interacts stochastically. In other words, the quantum system comes in, interacts with the classical system, and what comes out for the classical system is not some unique path, but it's a statistical mixture of possibilities, the same statistical mixture that you would expect if you were having the quantum system interact with a quantum system, i.e., in order to have a quantum system interact with a classical system, one has to make that interaction a stochastic interaction rather than a definite interaction. In order that, for example, Don Page's experiment would work. So one of the things that one can ask, and this comes to some extent from Bohr's concern when Bohr was trying to figure out what in the world does quantum mechanics mean and what does this probabilistic stuff in quantum mechanics mean. He started talking about dividing the world into two things. One is that you have the quantum regime, which behaves quantum mechanically, but then you have measuring apparatuses and so forth, which behave classically. And so there was implicit in his description, I mean, he's never very clear as to exactly what he meant, but there's an implicit thing in there that the world should be divided into a quantum part and a classical part. The classical part measures the quantum part, reduces the wave function and all of that kind of stuff. So then the question is, where's the dividing line? Since we certainly see the world around us as seeming to be classical, big things should be classical and small things shouldn't. Now we have an object that people have built over the last 20 years, namely LIGO, which is a huge thing, as we'll see. And surely, because it's such a huge thing, if anything is going to be classical, it should be classical. So one could ask, are the mirrors, for example, in the LIGO system classical? The mirrors are big. As we'll see, each one of those mirrors are 40 kilograms. Almost my size. Not quite, but... so the question is, are those mirrors behaving in a classical way? Can I use Jonathan Oppenheim's ideas in order to test whether or not the mirrors are acting classically or are acting quantum mechanically? And the amazing thing is that one can actually do this and come up with an answer. So this is just repeating that one had trouble, Bohr's discussions led to this, but many, many people throughout history have speculated that somewhere in the intermediate between atoms and us, systems change from behaving quantum mechanically to behaving classically. Not just due to decoherence, but intrinsically, that they are intrinsically classical, that big things are intrinsically classical. I.e., is there a limit to the validity of quantum mechanics? And as I say, many otherwise very good physicists have taken the position that there is. Of course, ultimately experiment decides. So here's LIGO. You've probably seen pictures like this before already, but let me go through them again. What LIGO is supposed to do is to measure the effect of gravitational waves coming through the Earth. One has these two very long arms. This is a Google Earth picture of the Livingston, the LIGO detector at Livingston, Louisiana. Each of these arms is 4 kilometers long. This line in here is not part of LIGO. It's an electric transmission line that runs right through the middle of LIGO, which of course causes some trouble because one has all kinds of electromagnetic interference due to that line that one has to filter out. It was also placed in the middle of a forest, and just about the time that they bought basically a few hundred meters on these sides of each one of these arms, because buying that whole piece of territory would be just far too expensive. So just as they finished it, a lumber company moved in who owned the rights to the lumber on this piece of parcel and chopped down the trees. You can see this bare patch here. Those trees falling down, of course, caused minor little earthquakes. And so they had to try and design LIGO so it wouldn't hear these trees dropping down. So what one has in LIGO is mirrors, 2 mirrors on each one of these arms, which form a Fabry-Perot interferometer. This mirror has a very, very high reflectivity of about, 6 nines, 99.999999% reflectivity. This one has a slightly less reflective, so that laser light can come in on resonance with this thing, and the laser beam builds up in each one of these arms. It in fact builds up so much that the intensity of light in each one of those arms is approaching 1 megawatt. That's a lot. You would not want to walk into that. That's enough to power a small town with electricity. The laser, there's a laser over here coming in, feeding in about 200 watts. Goes through this beam splitter, bounces off, and goes into these resonant arms. And the whole thing is tuned in such a way that the distance from this mirror to this mirror and the distance from this mirror to this mirror are exactly some multiple of a wavelength of the light separate from each other. So when the light comes back here, almost all of the light just goes back into this arm towards the laser. Well, you'd think, well, that seems to be a bit useless. But they've tuned it in such a way that these two things are not quite you don't quite get complete cancellation of this coming out of this output port. You get a tiny amount, milliwatts of radiation coming out of this port. And it's the fluctuations, in particular the intensity fluctuations of this output, that one finally measures and looks for fluctuations in that which are caused by the gravity wave coming by. Each one of these end mirrors looks something like this. It's doubled up. There's one thing. All of these are heavy metal. These two are heavy metal masses supporting two fused silica masses. These fused silica masses are about 40 kilograms each. That's duplicated here in order to be able to put some electromagnetic forces on this system. There's coils in here which you can charge up and which push this mass, push or pull this mass so that you can exactly tune things up. This is pretty amazing. If one looks, let me see if this is going to work. Whoops. Nope, it didn't. Okay. What happens when a gravity wave comes by, it, depending on its polarization, it will shorten this arm and lengthen this arm. I've got a little movie which apparently didn't get into this one. But in that movie, you can actually see those ends. Hello?
Okay, that's all right.
All right. Where you can actually see these ends going back and forth as the gravity wave goes by. One of them lengthens and the other one gets shorter. Of course, the whole Earth does that as well. And this would be what would happen if one had a gravitational wave which was of the order of 10 to the 21 times stronger than the ones that have actually been seen. Fortunately, one's never seen that bad a one because, of course, if one changed the distance on this 4 kilometers by, let's say, 20 meters, the ground this would be like a huge earthquake. The ground would crack and the lengths of the tubes would crack and all this kind of stuff. But that gives the idea as to what happens, and that's what one is trying to test. If these two end mirrors move in and out of phase with each other, then of course the phases of these two beams, when they come back to the beam splitter, will be slightly out of phase with each other, and much more, a little bit more signal will come out of this output, or a little less signal will come out of this output. And one measures that on the output stage here. Just to give you an idea, these are from the LIGO site. These are two of the end mass test mass, the end masses. They call them the test masses. This is one of the Fabry-Perot inputs here. In order to make things reflective or partially reflective, one cannot use the usual things that we use in mirrors, for example, coating them with a very thin layer of aluminum to reflect back the light. The aluminum just simply absorbs far, far, far too much of the energy. These are all done by interference techniques where you put varying dielectrics on the surface of the silica mass in order to produce almost perfect reflection from these mirrors, or for the beam splitter 50-50 reflection created by the beam splitter. But this gives you an idea of the kinds of sizes. These are, as I said, 40 kilogram masses of fused silica because it's amorphous and doesn't have grain boundaries, and those grain boundaries, big grain boundaries, tend to move and produce little earthquakes inside the material, which you certainly don't want. The laser beam occupies the center area of these masses. And the problem is that there is a tiny amount of radiation absorbed. And when you're bombarding it with a megawatt worth of light, a tiny bit is going to get absorbed, which of course heats up the masses. And that heating up the masses is not uniform, because you don't want any of the laser beam that you're using to measure the distance to go past the edges of this. You don't want uniform illumination by that laser beam. So what they do is that they illuminate this mirror with a carbon dioxide infrared laser, which can be absorbed. It's off the reflective resonance of all those dielectrics. And by putting just enough there, enough of that CO2 beam can be absorbed so that the effective radiation of those mirrors is uniform. And the shape of the mirrors and so forth doesn't get changed by all this horrendous light bouncing off of them. This is true for all of these mirrors that one has in the system. And this is the both the measured and the calculated noise sources of the system. These various lines are what one was able to do originally, and over the last 10 years or so, they've been improving the mirrors, etc. Here, this line here is quantum. What do I mean it's quantum? Well, the light that's shining on it is quantum light. And it produces noise of two different sorts. One of the noises is that when you measure the output from the laser interferometer, the measuring devices measure the number of photons that hit them. The detectors, the photodetectors, basically measure how many photons hit them. But we know that the light coming from a laser looks very much like a coherent state, and the uncertainty in the number of photons in any regime goes as the square root of the number of photons. That's a noise source. So, 1 second, a few extra photons come in, another second, a few fewer come in, and that, of course, looks like a fluctuating signal, which is going to hide the gravity wave signal. This is primarily a problem at high frequencies, but it's actually there at all frequencies. So this part of the curve is due to the so-called shot noise. But there's another form of the noise, which is the shot noise acting on the mirrors themselves. Namely, you have fluctuations in this light beam, and that 1 megawatt is going to have quantum fluctuations within it, i.e., which goes the square root of the number of photons that hit the mirror. You'd think, come on, 1 megawatt, how much could this fluctuation be? It's enough to completely hide the signal that you want to see. It falls off because, of course, the mass response to this force produced by these fluctuating number of photons, the bigger that mass is, the less it moves. And it's the motion of that mass that one is trying to measure. So this falls off as a function of frequency, certainly at a different rate than this shot noise falls off as a function of frequency. Most of this is because the noise is being measured in terms of the energy per octave rather than the energy per frequency bin. And as you get higher up in frequency, of course, each octave has more individual frequencies in it, and so the amount of noise goes up. And this forms a limit as to how accurately one can measure things. Now, one of the things that we notice is that as it was set up about 2 years ago, which is where this was from, at high frequencies, this noise source is dominated by the shot noise. These spikes are either 60 hertz spikes from the electric wires going on overhead, 60, 120, 180, etc. Or they're due to the vibration of the supports of the mirror. These are strings under tension. They're about 0.4 millimeter thick quartz strings that hold up the masses. And they're, of course, under tension, and so therefore, just like a plucked violin string, they have various frequencies in them. And most of these guys up here are due to those vibrations of the supports. But because they have such a high Q, they're distributed only over very, very, very narrow ranges of frequencies. And one can take them out even in processing afterwards. At low frequencies, there are two things. This branch here is primary. Where is it? This one is primarily thermal. It's primarily, where are we? Seismic. This green stuff, and notice how much that's been removed. If one didn't have all of the seismic isolation, this instrument will in fact detect the waves hitting the beach from the Gulf of Mexico on one side and from the Pacific Ocean for the detector at Hanford, Washington. You can actually see the effect of the waves on the beach producing noise in the detector. So one has to reduce that noise by a factor of about 10 to the 30th, 300 dB, in order to get rid of that noise. And there's various other, this red line here is primarily due to thermal motion inside of the dielectrics inside the mirror. So the LIGO is really only usable for frequencies above about 30, above about 30 hertz. Below that, all kinds of these other noise sources are far too intrusive. So, this is just absolutely astonishing that we have gotten the system with mirrors which are 40 kilograms to behave like a quantum system. And it does pretty well until it gets swamped by all of this other stuff here. But that doesn't tell us anything really about the quantum mechanics of those mirrors themselves. This looks at the quantum mechanics of the electromagnetic radiation, which we always knew was quantum. So let me make a very simplified model. This was a model that I came up with back in the 1980s when I was worried about quantum effects on LIGO and so forth of the gravity wave detectors. So here we have two possible inputs to this beam splitter coming from this direction or coming from this direction. Half of this one and half of this one go out this beam. Half of each of these go out this beam. Half of the energy in them goes out that beam. But the phases get shifted by this beam splitter as the light goes through the beam splitter. And it's that shifting of the phases that becomes important. We then bounce this off, and this model, this is a perfectly reflecting mirror. This isn't there in LIGO, because what LIGO does is have a mirror here and a mirror here. But as we know in LIGO, it's only sensitive to differential motion of those mirrors. If both of them move in or out the same amount, then it's not going to change at all what the intensity is coming out here, because the phase relationship between these back propagating beams will be exactly the same. So this is a system in which one has gotten rid of that common mode on those two ones, and this mirror, if the mirror moves back and forth along this direction, it's going to change the direction, change the phase of the two beams that are returning here, and you'll get more or less frequency, more or less intensity coming out of this arm than out of this arm. So this is just, doing the mathematics of the beam splitter and of the, this is the output in terms of the input. So this is, yeah. Now, what we get here is that first, this mirror simply reflects back the beam. If it moves, it's going to reflect back this beam a little bit earlier and this beam a little bit later, therefore changing the phase. The relative phase of those two beams, and when they come to the beam splitter, more or less intensity will come out of this part of the beam splitter. This looks at how the beam splitter operates, given an input, what is the output, and what are the phases of the output. And similarly, if we get a beam coming back in towards the big beam splitter, how much of it gets distributed in the two directions of the output of the interferometer. This just says that when these beams come and that hit the mirror, the back beam contains in it not only the original time and the original position, but also a term which depends on the position of the mirror. Now, in actual fact, of course, this term in here should be, again, t plus y plus twice z. And that z should, again, have a t plus y, get this infinite chain of terms. But z is, by assumption, so small that if you square it, it's completely negligible. This is what I'm saying here. This term should have a z in there, and then it should have another z, blah, blah, blah. But by assuming that the motion of the mirror is terribly small, 10 to the minus 21 or 10 to the minus 23 kilometers. The square of that is completely negligible. So that's how the mirror acts, but one can also look at what happens to the mirror. The mirror's motion is going to be d squared z by dt squared. This is just a harmonic oscillator. And in this case, I've assumed that the restoring force of the harmonic oscillator is 0, which it's a pretty good approximation to, because the actual motion of those mirrors on their hanging from their threads is of the order of 3 hertz, which is well below the frequencies at which one is doing any measurements. So as far as the measurements that are being done up around between 30 hertz and a kilohertz, simply don't see those mirrors as being free mirrors. These are the radiation pressures on the mirror, one coming from one side and the pressure coming from the other side due to the light. And that is, psi is the light field, and the light field acts like a scalar field. The single polarized, it's singly polarized, acts just like a scalar field, which has quantum fluctuations in it. And one can calculate those p's on the two sides and finds that they're different from each other. Then you have the detection at the far end, and this is one is measuring the photocurrent in the diode, which measures the flux of photons, and that behaves like this quadratic expression here. This is the current, the light current that comes out of the interferometer that one is measuring, and it's also a nonlinear thing. It's basically measuring the number of photons. The incoming field is like a coherent state. It's got some classical value, alpha, and it's got quantum fluctuations in it. And my assumption is that those quantum operators are all tiny with respect to the actual state. Nanowatts versus megawatts. They differ by many orders of magnitude. A and B are the annihilation operators coming in from the y direction and from the x direction. The input from the bottom is supposed to be, those are supposed to basically be the vacuum state, and this is these A's. If you had A equals 0, that would be like the vacuum state, but because that field has got this constant alpha in there as well, the actual field is extremely strong and the quantum fluctuations look negligible. One of the problems of this thing is that it really isn't 0, because making a laser that produces only one single frequency, namely as this alpha, is impossible. One will have both phase fluctuations and amplitude fluctuations in the incoming laser beam, which one can model as being these A terms being not the vacuum operating on the state, A operating on the state being 0, but A operating on the state being some small fluctuations. Now, they've done an absolutely incredible feat of reducing these, but that still would produce excess noise if one got some of that A getting into the output. Well, these are just what we choose the phase of the two beams to be such that e to the I omega, where omega is the frequency of the beam, is equal to 1. And we can therefore approximate things by assuming that Z is small. And when one goes through that, one finds that the output has two terms in it. One is due to the motion of the mirror, which is what one wants to measure. This is multiplied by the intensity of the beam plus a tiny little offset. In other words, we offset the mirror from its 0 point by a tiny amount so that there's a little bit of light that gets through. And we need that in order to be able to see the motions of the mirror. Plus, what comes out of the output port is again what went in, namely these B operators. The B operators are the annihilation operators and creation operators that came into the output port. Now you'd think, well, what one wants is to have those to be equal to 0 so that one has the vacuum state coming in. This realization that the noise the quantum noise that one gets in a laser interferometer comes from the output port, not from the input port, was realized by Carl Caves in 1980. And so it's this term that's responsible for all of that quantum noise that one saw in those diagrams. So one has the shot noise, which comes from the bees, also the radiation pressure noise, which actually moves the mirror themselves and comes in through the comes in through this. So there's a source of noise, which is the radiation pressure noise, which comes through this term, and there's a shot noise, which comes through this term. But the radiation pressure noise also turns out to be coming from those B terms. The pressure exerted by the A terms are symmetric, and so they just cancel out and don't push on the mirror at all. However, the radiation pressure of the B noise is the lowest order of opposite signs on the two mirrors, and they don't cancel. Furthermore, the shot noise and this radiation pressure noise are conjugate variables. One is B plus B dagger, and the other is B minus B dagger, if one actually looks at the noise. So these are complementary terms. If one reduces the shot noise somehow or other, one increases the radiation pressure noise. If one reduces the radiation pressure noise, one increases the shot noise. Now, one could say, well, in large parts of the response, the radiation pressure noise dominates at low frequencies, and the shot noise dominates at higher frequencies. And so there are regions in which one doesn't have to worry about either the shot noise or you only need to worry about one. But the most interesting place is down around about a kilohertz, down about 100 hertz. Both of them are of roughly equal size. And so anything you do there doesn't make it better. So here's the force on the mirror, which is B plus B dagger. And this is this 1 over nu squared. Nu is the frequency of the electromagnetic waves coming in. Omega is the frequency of the harmonic oscillator, which was 3 hertz. This term means that the radiation pressure noise dies off as you go up in frequency. Oh, this is just repeating what I said. So how does a detector work. Glauber in the 1960s argued that a photon detector basically measures the flux of energy coming, the operator is the flux of energy, which can be expressed in terms of B plus B times B dagger, the number of photons in the system. So one of the terms looks like this. The other interesting thing about the radiation pressure noise is it also has a term in it which is not just the annihilation. If one looks at the annihilation operator coming out into the detector, it's made up not only of the annihilation operator of B, of course, of the B annihilation operator, but has both components. That's the typical behavior of an amplifier. So the radiation pressure noise acts like an amplifier and introduces more noise by squeezing the field that comes out. There are things called two-mode squeeze states, where if you have, C and C dagger, C and C tilde are two modes of, let's say, the radiation field. If the output is equal to C plus rho times C plus sigma MC dagger, then one gets additional noise. The commutation relations D and D tilde had better commute to be 0, and D and D dagger had better commute to be 1. And you get these relationships between the sigmas and the rhos. And that's exactly what you get in an amplifier. So LIGO acts as an amplifier of the noise, not what one wants. The two noise sources simply add onto each other. Now, quantum mechanically, we know that if you have two quantum systems, two quantum states adding to each other, that's just another quantum state. And what one gets here is a squeeze state, and it's this thing that one would like to be equal to 0 to make the output of the interferometer have as the least noise that one can. And if one has the B field, the incoming B field, not being the vacuum state, but instead being one of these two-mode squeeze states, one reduces the total noise that come out of the system. One can reduce both the shot noise and the radiation pressure noise at the same time. It turns out that the amount of squeezing, denoted by rhos and sigmas, has to change as a function of the frequency nu, but that's possible. And in fact, that's exactly what people now do in the newest version of LIGO. They attached a whole new system onto it, onto LIGO, in order to feed noise into the input of the interferometer. You say, that's nuts. If I feed noise in, it's going to make things worse. I mean, I can't make things noisy and make them better, but quantum mechanically one can. And this was tested about 2 years ago. And here is the radiation, here's the quantum noise on this was on a test thing. This was the best that one could do as far as the noise sources by squeezing operating on the by feeding in the squeeze stuff, which minimizes the shot noise, you increase the radiation pressure noise, which is what happens down here. But if you choose that squeezing in the right way, lo and behold, one can reduce the noise on both parts. And in particular, in the center, where both the radiation pressure noise and the shot noise contribute, one gets a severe reduction of the noise in the interferometer. This was so promising that they immediately went ahead and designed a whole new system to add on to both the LIGOs at Hanford, Washington, and at Livingston in Louisiana, and reduce the total noise source in the system, so that the sensitivity improved by about a factor of 2. And they're still doing more work that they can do the squeezing better, and increase it by even higher, by even larger factors. So what one finds is that you have, for the quantum system, one can reduce the noise by feeding in noise. Now, this is all quantum mechanics. What would happen if the mirrors were classical? Well, then your intuition would be right. By feeding some noise into the input port, you would increase the noise coming out of the output, not decrease it. This decrease is due to quantum interference between the two states that one is looking at, between the shot noise component of the state and the radiation pressure component of the state. One can cancel that out because it's a quantum system. As we know, with a quantum system, if I shoot bullets, if I have somebody else shooting bullets at the same target, the target gets more bullets no matter what I do. On the other hand, if I do it quantum mechanically, then if that target happens to be at the minimum of the interference pattern, the number of bullets decreases instead of increasing when somebody else shoots. If they shoot at exactly the right, they shoot in exactly the right quantum state. And that's exactly what's happening here. So the fact that LIGO has now gone ahead and converted their system to the quantum mechanical statement that one can reduce the noise by feeding noise into the input port of the interferometer tells us that that interferometer is acting classically, not quantum mechanically. You could do semi-classical, it corresponds to the expectation value of the quantum force. But the quantum force is proportional to the operators B and its conjugate. Those expectation values are all 0, so they shouldn't have any effect whatsoever. So this has never been a serious contender for classicality. In stochastic gravity, as Jonathan Oppenheim, for example, has been exploring, one can do this. One can have the mirrors be classical and the rest of the system be quantum. But again, the noise adds instead of being canceled by interference type terms. So the fact that LIGO works precisely means that the mirror is responding to the electromagnetic field quantum mechanically, not classically. Those mirrors are quantum systems, not classical systems. So what we have here is that we've got a 40-kilogram object. That's big, 120, about 100 pounds, if you will. And that's behaving in the LIGO system as it were, as if it's responding to the electromagnetic field, which is a quantum system, as if the mirror were a quantum system as well. So this was the graphs from those tests that they did. So these 40 kilogram silicon dioxide objects are quantum systems. So this whole question of, is there some dividing line between classical and quantum? The answer is that whatever, if there is one, it has to be well beyond 40 kilograms. Now you could say, well, maybe it's not the weight or the mass that's important, but maybe it's the displacement. And it's certainly true that this displacement, the quantum displacement of those mirrors, is really, really tiny. And so that is not a good, if classicality only depends on, the quantum fluctuations being sufficiently small, then LIGO does not test that. But if it has anything to do with the mass, then LIGO is a very good test of that. And the answer is that these objects are quantum, not classical. So the delta Z, the quantum delta Z is about 10 to the minus 16 meters. So there is still room for creating a theory which is quantum for small distances, but classical for large. But it's getting more and more difficult to do that. If your theory is one in which the system acts in the same way as a quantum system does for short times, i.e. seconds, maybe it could still pass the LIGO test. But I think formulating a theory like that is really hard to do. So my conclusion is that LIGO is quantum. This does not mean that LIGO is measuring quantum aspects of gravity. The gravitational field that's coming in to excite the system that they've detected has about something like 10 to the 30 gravitons per cubic wavelength. It's classical. It's a classical signal coming in that one is trying to detect. Any quantum nature of that gravitational wave itself is way, 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 way down in the noise. There's no way in which LIGO can do that. But what this means is that LIGO itself, the parts of LIGO, and in particular the mirrors, are I apologize. Anyway, at this point I have to quit. I've more than taken up my time. I apologize about that. Yeah. That's the end.
We have some time now for questions or comments.
I have one. Hi, Bill. That's George Maxas. Glad to see you. And
Good to see you. Well, I can't really see you, but
okay,
No, there you go.
thank you very much for your talk. So let me see if I understand. So you're saying that quantum mechanics is necessary in order to explain LIGO. But by saying that LIGO is quantum, are you implying that we can superpose, make a spatial superposition of LIGO mirrors?
yes. What is happening is that you are superposing states of the mirror where the mirror is here and mirror is 10 to the minus 16 meters away from it.
And,
That superposition between those two guys is quantum.
and why can't we think of this superposition as being superpositions of phonons that are hosted by
Of what?
I mean, why can't you interpret this as a superposition of phonons that are hosted by the mirror?
Well, remember that, I mean, I don't know whether or not that you're looking here at the center of mass of those mirrors. There are no phonons at 3 hertz inside, or at even 100 hertz inside those mirrors. The lowest phonon frequency inside those mirrors is going to be something like, many, many kilohertz, not down around 100 hertz or 300 hertz. So, there are no modes in the mirror except the center of mass motion, which have such low frequencies.
Okay, thank you.
Other questions or comments? Here?
Hi, Bill, thank you for your talk. I have a question about the first part where you were looking at this harmonic oscillator and this.
Right.
And of course, you're correct saying that individually neither the little p or t or big P and big Q commute with the constraint, and thus sort of their ontological status is ambiguous because they're not gauge invariant. But then you write down this Q, or I forget exactly what it was, this linear combination of sine and cosine of t, talking about the trajectory of the oscillator.
It's not.
Sure.
It looks like the trajectory of the oscillator, but it's not, because none of T, Q, or P are actually physical quantities.
Right, but that combination, if I understood what was showing, that does commute with the constraint, yeah?
Yes.
And so then, is it not fair to say that that observable corresponds to a simultaneous measurement of the position of the oscillator and the clock time, for example?
You cannot make those measurements of the simultaneous measurement of T, Q, and P, because T, Q, and P do not commute with the constraints. They're not physical. They're not measurable. They're gauge dependent. Where the gauge transformation is the thing given by the constraint.
Right.
So that's like saying, well, if I go in and I measure A, the value of A on my desk here, just on my desk here.
But maybe just to push
And I look at you and I say that makes no sense, because A is not a gauge invariant quantity.
But can you say that you're measuring A at a particular time T? So
No.
the thing you ever actually measure is A when T.
No, in electromagnetism, the gauge transformation, of course, is the usual phase transformation of the fields, etc. A plus divergence of
Or the electric
arbitrary scalar field.
Okay.
A doesn't mean anything. So you can't measure. I mean, it's not a physical thing that you can measure. You can only measure gauge independent things. So you can measure E, you can measure B, you can measure integrals of A around closed loops, but you cannot measure
I think Henry has his hand up.
Yeah, just to comment on that. So I agree with Alexander in a way. I agree with you as well, Bill. But A by itself, or in this case P and Q, might not be an observable. But that doesn't mean you cannot mention them when describing observables. So you mentioned the electromagnetic field. You can write it as a antisymmetrized derivative of A. So
yes.
You're using A, which is a non-observable thing.
Oh, sure, and that's
a gauge invariant thing.
That derivative, the antisymmetric derivative of A, which is E or is B, is certainly measurable. That's gauge invariant in that case.
Right, and so
okay, but none but A itself doesn't mean anything because it's not a gauge invariant quantity.
Right,
So you cannot say, you know, the A over there is 37. I go there and do your measurement and I say, what are you talking about? It's 943. And your friend comes and says, oh, you're both crap. It's 25. You know, all of those are possible values.
Right, but what he's saying is, if you're not measuring just P or just Q, you're measuring a combination of both, just as you would not go and measure A over there, you'd measure the symmetrize, how A varies in a direction.
So that whole thing, P, Q cos over cos T, capital T, etc. That thing is gauge invariant. That thing is measurable. I agree. But you cannot then interpret that as that tells us what P and Q are at the time T. That's what makes no sense because P and Q and the time T, none of those are measurable quantities. So you're saying that I'm interpreting this 5 that I measured for this whole thing, I'm interpreting that as being the value of P and Q and T at some particular time. Makes no sense because P and Q and T are not measurable things. If I try to measure them, I can get any value I want simply by doing a coordinate transform, by doing a gauge transformation. So it's like saying that I'm going to imbue A itself at a point with physical significance, and as we know, we can't do that. We can certainly do this antisymmetric derivative. It has a physical significance, etc.
More questions or comments now? No. So let's thanks. He wants to compliment something.
So just to get the punchline a little bit clearer, you mentioned the Oppenheim's post-classical, I forgot the exact name that he gave to it, that John gave to it, but so the message at the end is that this puts this idea under a lot of pressure. It doesn't disqualify it. It doesn't, but it puts it under a lot of pressure. It controls its space of parameters in some way, or is that the final?
That's true of all experiments.
Yeah.
No experiment ever rules out completely everything except one particular theory. Experiments always have, sort of loopholes in them where if I change it this and this and this and this, maybe that's a possibility. Of course, one would have to do an infinite number of experiments in order to completely rule out all possibilities. But at a certain point, you just say, Newton's laws are good, and then you discover that if you do very, very, very accurate measurements, Newton's laws start looking a little shaky because of quantum mechanics.
Right. So let me make that more precise. Does this result make you discard Jonathan's theory, or think it's not promising?
Discard
the post-classical, Oppenheim's theory.
Right. Yeah, I mean, for me, it is at least one bit of evidence, knowing that we are not going to ever be able to measure the actual quantum nature of the gravitational field itself, or as Trump says, never say never. But it's going to be extremely difficult to see actual gravitational effects of the gravitational field itself. But this, I think, puts, as you say, a lot of pressure on people who believe that there is some, that there is a difference, that there are some things which are behaving classically and some things behaving quantum mechanically. Here we have something which is like us, and it's behaving quantum mechanically. Not, one could show that it couldn't be behaving classically. Now, it's an incredibly special thing, right? None of us go around with LIGO in our pockets and saying, look, here, this is quantum. I mean, it takes a huge amount of effort, many, many, many dollars to get to a regime in which one could do this kind of a test and show that those mirrors are behaving quantum mechanically. But that's the way of physics, is you do experiments and then those become, fixed points that you have to always try and work your way around and make sure that your theory, whatever it is, explains those experiments, because, experiments are at the heart of all of physics.
So can I just follow up with one? So in these ideas by Marcus Aspelmeyer and a lot of people around the world, like in Vienna especially, but all around, to have experiments that test gravitational superposition directly of masses. So quantum superposition of gravitational masses. Would something like that disprove Jonathan Oppenheim's theory already? A positive result in an experiment like that disprove?
If those experiments actually got the results which contradicted quantum mechanics, then of course. On the other hand, I am extremely skeptical about any of those experiments actually working.
Any more questions or comments from the audience? Okay. So Professor Unruh, thank you very much for your participation. Let's thank the speaker again.
Thank you.